Dorodnitsin. So as you can see from the transparency, I will speak about the problem of the applications of the approximate methods to the quite general problem of stellar stability and gravitational collapse. In fact, this work is motivated by the several still unsolved problems of general astrophysics. Since these questions are quite known, and for the first look it may seem that we know answers on it, but in fact there are only a few reliable answers and results are obtained so far. The questions actually are the following. What is the collapse behavior of the star at the final stage of its evolution? Namely, what is the picture of the collapse of the star? And in fact, even the problem of stability, there is many things to do in that field. So it is very easy to obtain via known techniques the equations of the star stability and gravitational collapse. But it is inversely proportional to we have to pay that in fact it is very difficult to obtain the numerical solution for somewhat realistic cases. In that order, it's moreover important to develop an approximate method or different approaches which will let us to obtain the rapid answer on such questions like what will be the comparative neutrino light curves, and actually what will be the collapse picture. Since, as I have mentioned, there is only a few reliable answers on that question are obtained so far. In fact, these equations are extremely sensible in part if you want to get this exact solution numerical, somewhat you can rely on. It is extremely sensible to the particular equations of state. That's what I mean, that it was solved only on just for a few particular equations of state, and that's the motivation. The application of the Galerkin method, now I'm skipping to the end of my talk, allows to investigate stability with much more precision. In fact, if speaking about the variational method of investigating the stability, it allows to obtain the trial functions with very good precision. In fact, it is possible to obtain them with arbitrary precision. In case of the collapse, the Galerkin or Galerkin-Ritz methods allows to obtain the picture that described by the set of equations of ordinary differential equations. Of course, it is extremely obvious that it is really possible to solve such system, and this system can be solved for quite various set of realistic equations of state. And since the first schedule of my talk was at the very end of the morning session, I consider that most of the people will sleep, and so that's why the first of my talk will be probably even tutorial. So I beg pardon of the audience, but I think that such an introduction can be somewhat necessary. So also I begging pardon of mathematicians that I'm skipping some necessary mathematical conditions in order to clarify the whole picture of what is that. So actually Galerkin method was introduced by the Russian engineer, mathematician, and physicist, somewhat about 50 years ago, Galerkin, in the province of Russia. He wanted to solve a particular problems of mechanics, but he has actually no tools for doing that. That's why he introduced the method that now is considered to be the most general method, approximate method of that field. Actually, all methods like Ritz methods and so forth are only the subset of this method. In fact, it is extremely simple. In the original representation, it was the following. If one wants to solve the differential equation, whether it's partial or ordinary one, and of course he can't do it, since that's why we need the approximate method, it goes, instead of solving the initial problem, he converts it to the problem of finding the minimum of the corresponding functional. Actually, since we don't know the trial functions, of course, it is almost the same difficulty we encounter in solving such a problem. But in that case, we need to expand the solution when finding the minimum of the corresponding functional that will give us the corresponding equation we want to solve. We expand the solution over the series of some, let's say, good functions, good analytical functions. Of course, it should satisfy boundary conditions and so forth. In that case, this corresponding functional became, and in fact we expand the solution, and now, since phi is known as a set of known analytical functions, the problem reduces to the simple problem of finding the coefficients. And the corresponding functional became a simple functions of several parameters. And instead of solving the variational problem, we need only to get the minimum of the function over the alpha. So, in astrophysics, there's actually, and not only in astrophysics, there are actually only a few ways to investigate, only two ways to investigate the stability of the star. The first, this is okay. Of course, I will explain it. In fact, two methods can be used. The first is perturbative, and the second is variational. Here, I will speak about the variational method. It is well known that in most cases they are equivalent, but the perturbative method yields to the quite difficult problems of finding the problem of finding the eigenvalues of the Sturm-Liouville problem. And of course, for the most realistic cases, it is extremely difficult to obtain such eigenvalues. I will remind you that the positive eigenvalues will correspond to the stability of the star, and the negative will mean the onset of instability. So here I will consider the generalization of the energetic method. As I've told you that the first part I will describe it in as simple as I can, and at the very end I will skip to the really results which are somewhat new. All these results, of course, are not new, they are 40 years old and so forth, but still. So here we have the energy functional of the star, whether it's Newtonian, when it's very simple, or whether it's general relativity. And since we don't know the trial functions, we are expanding some functions, or whether it will be the displacement or whether it will be the density in case of the Newtonian star, and of course in case of general relativity star you have to use somewhat that differs from the density. It's better to use concentration or the rare density. So for the trial functions we choose the known profiles obtained as simple functions as we have, namely the Emden profiles. So for the zero function we use the Emden profile, and for the the rest functions, we need the combination. In fact, here I met the trigonometrical, the simplest way, the simplest way to obtain such an extension. Here I will remind you what is, I think everybody knows, of course, but I will remind what is the Emden profile, since it's really, I think, oops, yeah, here it is. So, in fact, Emden profile means the following. Let's consider the Newtonian star, and if we will combine the equation of static equilibrium of the star together with the continuum equation, and then skip to the somewhat special coordinates, somewhat special variables, we will get the well-known Emden equation that can be numerically integrated. And actually, here we immediately get that if the polytope index is 3 or the gamma is 4/3, the total mass of the star does not depend upon the central density. It is namely the Chandrasekhar limit and everything that is connected with it. And we immediately get the velocity profile. And in any case, using the boundary conditions, it can be solved to obtain the profile of the density and of all the functions inside the star. In reality, if you will make all these calculations, you will obtain that if the density is extended in this way, only using the central density as a parameter, you will obtain the profile of the density like this. It's well known. Actually, in energetic method, here I'm going to the energetic method, was also developed about, I don't know, 4 years ago by Fowler and Zeldovich in order to obtain all this picture in the first order. So it is namely the following. If one has the energy function of the star and wants to know when the onset of this instability will occur, it will obtain the following result, that the necessary condition of the stability is the 0 first variational derivative of the mass energy of the star. The positiveness of the second order partial derivative will yield the stability. But in fact, this problem is also very difficult to solve since the trial functions are unknown in this variational problem. And here we use the Galerkin method to simplify it. So we require the minimization of the mass energy of the star with one condition: the entropy per baryon, the entropy distribution per baryon throughout the star should be constant. That's very important. In static case, and in static case, when we do not consider the dynamical processes, the problem reduces to the very simple problem of finding alphas from the set of the algebraic equations. So actually, the state of art of all this Galerkin method is how to choose, of course, these functions of what we use in an extension. So actually, but if you are able to choose the good set, the answer will come immediately. And in case of a static case, I say that's extremely simple. The requirement of the positiveness of the second variational derivative yields corresponds to the positiveness of the corresponding eigenvalues of the problem if we would solve it in perturbative method. In case, actually, when we use only one term in that expansion, that will give us the classical energetic method, how it was used by Fowler and Zeldovich. But if we use somewhat 2 terms and 3 terms, it appears that it gives very good precision. Only two terms gives very good precision if using these techniques with Emden profiling functions. So if we use two or more, the this condition will become the positiveness of the quadratic form. That means that all the determinants should be positive and all its minors should be positive. What configuration do you mean? Yes, of course, that's true. Of course, that's a real problem. But fortunately, here we have many exact solutions for the cases of Newtonian star and for the post-Newtonian star. Even in general relativity for the static case, it would be a bit more complicated technically, but we can obtain Emden profile for the static configuration. So we will expand functions of dynamical problem on functions of static one, and then after matching somewhat exact known, since we know a few exact solutions, so matching these exact solutions, we will adjust these functions, and that's why this is, fortunately here we know some functions, but of course in general it's difficult. In case of, I would like to mention quite an interesting thing, that in case of post-Newtonian star, even not the equation of stability can be obtained, but also the equation of the collapse. Since if you use one term in that expansion, over the parameter will be the central density. Using all these profiles and all these techniques, one can obtain the dynamical equation for the central density. Since it is, I will remind that I'm speaking about the post-Newtonian star. Since here it is quite simple. This equation is valid for the post-Newtonian star with one GR term. That was obtained by Bisnavat-Ekogan in 1968, I suppose. And it gives really interesting correspondence with the exact solutions. In fact, it gives an amazing precision. Even such simple method gives an amazing precision. Now I'm going to more GR and will tell what is the problems in GR. Unfortunately, here the mass energy, here I'm considering first the static case, and I will show how this method works in total GR. The total mass energy of the static case is represented as in a well-known form. Of course, the rest mass density should be included in the internal one, into this E. As a Lagrangian coordinate, as an independent coordinate, we choose the Lagrangian one, which is namely the number of baryons inside the particular sphere. So the idea is the following. We consider the Lagrangian sphere with a particular, let's say, Lagrangian mark, and observing how the energy, mass energy inside the sphere varies when the little displacement occurs. And the zero variation will give us stability. That's the physics. Unfortunately, the problem cannot be solved directly, since here in GR, if to go from here to introduce the independent variable, which is Lagrangian one here, it will be the same form. So you can see E here and E here. So the variation of this functional can be obtained only if applied the variational derivative to the corresponding differential equation. So what is done? From here, taking into account the definition of the number of derivatives inside of the Lagrangian sphere, the following differential equations for the variation of the mass energy function could be obtained. Then it is a simple ordinary differential equations for the variation of this mass energy of the star. Taking the book, where immediately, or if one wants, write it by hand, we immediately get the answer. So the first variational derivative of the mass energy of the mass energy of the star will be represented in this way. This is a necessary condition for the stability, but it's not enough. The onset of instability will occur only when that will be negative. So we have to check every time whether it's positive or not. The second order functional derivative is obtained the same way, from taking the second order and obtaining the solution of the corresponding differential equations. So here we are going to the final step, whether it works in reality or not, at least at the very little part of this reality. So how we can check it? We have the well-known Oppenheimer-Volkoff equations of state. That is namely the solution for the neutron star, pure neutron cold star, made from the neutrons. Actually, the thing I didn't say that if equating this to zero, immediately from this part you will get the static equilibrium Oppenheimer-Volkoff equations. So in fact, if one will integrate the Oppenheimer-Volkoff equations, it was done in 1939 by Oppenheimer and Volkoff. He would obtain that when increasing the central density, the mass of the total configuration will increase until some moment when the derivative will be negative and there is no stable configurations here. In fact, this is quite known. The distribution of the density will be like that, and since we need the distributions of all thermodynamical functions over the Lagrangian coordinate, it will look like that. Here so this is the Emden profile. This is very similar profile of the Oppenheimer-Volkoff. So what I'm saying about that, we can calculate all these models checking the positiveness of that thing. When it will become negative, we will obtain the exact point when the stability will break. If we will use Galerkin method here, so here we know one point when exactly the stability losses. So and if substituting here the expansion over the series of the functions I mentioned, we can adjust these functions and to see whether it gives really this point or not, since we know the exact answer. And it appears that these two functions which I mentioned, namely the Emden one and the trigonometric one, simple trigonometric, gives an amazing precision. So actually, it is many terms are after the point. Okay. So this example shows that this method really works, even in case of stability analysis. Here I'm coming to the also very simple mathematics that now we are trying to derive the dynamical equations, the same one as I mentioned for the post-Newtonian case, where it can be developed by using this technique, but in general relativity. In fact, here, of course, it's a bit more complicated, since we have a pressure in the star. This is a real star with a pressure, but the matrix is represented in the following form. One point I have to mention, that here we do not work in the comoving coordinates. We work in the earlier coordinates, not in the Lagrangian one, since all this mass energy was written in the earlier coordinates. In fact, in dynamical case, the mass energy functional is represented using this relation, where T00 is, of course, zero components of stress energy tensor. And so, as I told, that we work in earlier coordinates, which are namely the earlier radius, some earlier time we have to choose in most convenient way, and the velocity field. The number of variants, of course, is still the same relation. In fact, we determine the physical velocity of the physical velocity that will be in this stress energy tensor as a displacement, physical displacement, measured by the earlier observer, of course. It is only the definition. The all techniques is extremely known. It is, everybody knows it from the university. It's written in Landau lectures how to do that, all this stuff. We can, for such velocity, we immediately calculate the stress energy tensor, and now we have to take have to solve the same variational problem. But unfortunately, here it is two-dimensional problem. Previously, it was only one coordinate, Lagrangian one, and here it is a time. Now, unfortunately, these equations become partial ones. So we have to take the variational problem here. Okay. The velocity distribution here, after we would have to do something with the system, the profile of the velocity is here. We're speaking for the profile of the velocity, since we already paid by expanding of the density. We lost 1 degree of freedom, and now we have, it is somewhere here, the velocity profile. But velocity, of course, is somewhat connected with r dot. So the r dot can be obtained only from the second equation by differentiating it. After making simple calculations, we will obtain this equation for the r dot. But unfortunately, it contains the E dot, and E dot should be calculated as also. The E dot is obtained from the first equation. And so, of course, finally we will get the infinite set of equations. But the velocity profile, of course, is here. In all these calculations, I didn't write, but we implied that we already expanded the density, the concentration or density of the basis we have chosen. So we get the equation for E2 dots and so forth, and get the infinite set of equations. Of course, it should be cut on some step to get the somewhat, since we are not interested in obtaining some equations, we want to get some number for somewhat picture of the colors. It should be cut on some step. Also from the calculations, and it's really quite obvious that the final stages of the collapse, whether it's a neutron star or whether it's a supergiant star, it's only the difference of equations of state. In supergiant star, the entropy is so large that the pressure is dominated by the radiative pressure, and the onset of instability is due to pair formations and so forth. But actually, the physics now, this kind of physics, we're not interested now. But the final stages will be very close to the free fall. Anyway, free fall of the dust spherical cloud. So the energy is so high. Actually, the influence of the pressure, the gradient of the pressure is negligible. So it's very close to the free fall on the very final stages of the collapse. So in order to get the real number, we the one way to cut the system. There is an infinite ways to cut the system. Is to take, for the cutting, to take the solution from Tolman one. In fact, for instance, for the dust spherical clouds, it is obvious that since there is no pressure and the gravitation from the physical point of view is something that is out from this particular sphere with Lagrangian radius, it is extremely simple. So the E dot will be zero, for instance. This is the most simple way to cut the system. So if there is no pressure, the E dot will be zero. If there is some pressure, the E dot, that is namely how it changes in the time the energy inside the Lagrangian sphere, it is somewhat about the work of the pressure on the border. So the one way is to choose the Tolman solution. Okay. So I think I will leave it here. So the idea is the following: that why so many difficulties in GR and why it is so simple even in post-Newtonian case. From the physical point of view, it is namely the following: that in all classical cases, the kinetic energy cannot be splitted out from the total mass energy of the star. That's why we can take some times derivative from it. But of course, in general relativity is embedded into the stress energy tensor. That's why it's so difficult. So the velocity distribution inside the sphere also determines the gravitation, of course, and also determines the variation of the mass energy of the star. That's why it's difficult. So actually, we did all this, but I cannot say that we made the numerical calculations also in the case of the collapse for also simple equations of state, that is, namely the Oppenheimer-Volkoff-like. It also showed a good agreement, not so good as it was in the problem of stellar stability, where the precision was enormous, but also it was not bad. But this work is at the very beginning. Finally, I'm going to the conclusions. The talk was really very simple from the mathematical point of view. So, in order to obtain the picture of the collapse when using the energetic method generalized to the general relativity, we have to expand some trial function. What we did, it can be density, it can be the displacement, or whatever you want. That allows to investigate stability of by finding approximate eigenvalues and eigenfunctions of a set of algebraic equations which are linear, in fact, instead of finding the same eigenvalues from the second order derivative, the second order differential equations that will be in perturbative method. I would remind you that in perturbative method, this problem is extremely difficult to solve in realistic case. And that method allows you to find an approximate eigenvalues, in fact, with as good precision as you can choose the basis. In that case, the trial functions, whether it is displacement or density, may be determined with quite arbitrary precision. In the particular paper, the Oppenheimer-Volkoff equation was used to check whether it works or not and to adjust the corresponding basis. In case of stability, this work still have to be done. The equations that were obtained are in total derivatives, which is, of course, really much easier to solve for the realistic equations of state. But we have to, of course, we have paid by this. And in fact, it allows to get the rapid answer, about the picture of the collapse of whether it's neutron star or whether it's supermassive stars 10 to the 4 solar masses, and you can get the neutrino light curves on whatever you want, and I think that's enough, and that's all. Clear, I think. Excuse me? Okay. This one. This one? A is an independent variable. It is simply the analogy to the Lagrangian. It's the Lagrangian variable. It's in the for instance, the number of variants. It was okay. One moment. That's quite known. Of course, it's like this. It's blah blah blah. It's here. The only difference is, of course, of this coefficient with the Newtonian case. Yeah, I'm looking for the particular sphere with the Lagrangian mark. So I'm looking whether the mass energy inside of it is varying. That's the idea. Oops. Okay.
First of all, let me thank the organizing committee for my invitation. Unfortunately, I didn't work actively in this area, so for this reason, my lectures contains only two parts, introduction and discussion. But there will be a lot of introductions, and as to discussions, I'm going to consider some general properties of this approach of the Grad-Shapranov equation. And the main point will be the exact solutions. But unfortunately, I understood it's possible for me to discuss only one case, the particle-dominated case. But in this example, we will see how it's possible to determine all characteristics, the main characteristic of the flow. Very briefly, the private introduction. I was the last student of Professor Seravatsky, who died 20 years ago. He believed in exact solutions, and he explained us how the exact solutions help us to understand the whole problem, how it creates our intuition. And for example, he explained us how only the counting of the boundary condition, how many boundary conditions is necessary to solve the problem, give us very important information. So, in some sense, I'm going to count the number of boundary conditions in this approach. Next point, actually I have 5 2-hour lectures, so let me sorry for random enumeration because I use the transparencies. Very briefly, the astrophysical introduction. As you know, a lot of compact objects, extragalactic nuclei and young stellar objects and radio pulsars and many others have, in some sense, rather similar properties. That is, for example, extragalactic nuclei when we have jets, and actually the same picture for jets from young stellar objects. And it's another example, well-known example. And there is example microquasars in the center of our galaxy. And the main problem here, of course, is the energy source, mechanism of energy loss, jets, and in stars, for example, the disk formation, nature of particle acceleration, and stability. And the main electrodynamic idea is that the energy source is rotation of central body and accretion. Energy loss is actually the ampere action of electric current. Jet formation is attraction of parallel current, acceleration by electromagnetic field, and stability is the stability of rotating body. And so if we have, for example, in the case of the black hole, the regular colloidal magnetic field, so it's possible to introduce the flux psi. And if we have the rotation, so theta component of the electric field isn't equal to 0, and if we have the electric current flowing in the system, that is, we have toroidal magnetic field, it is possible to extract energy by the flux of Poynting vector. Another picture of this case, that is, there is the direction of the toroidal magnetic field and electric field. So we have the flux of electromagnetic energy from both poles. And the main problem here is that it's necessary to understand the nature of regular colloidal magnetic field and to determine the angular velocity. Okay, that's enough. Thanks. To determine the angular velocity, omega f, and to determine the electric current, which takes place in the expression of the total energy loss. I'm not going to discuss the first point, but two other points will be the main topics of my lectures. And of course, there is a fourth question. The validity of this approach to the black hole was the topic of the Pansley paper, Pansley talks. And of course, it's not clear that it is the magnetic field lines penetrating horizon that plays main role. And maybe the black hole has a passive role of the accreting center only. Okay, this is the end of my astrophysical introduction. And now some words about the physical introduction, the method of the Grad-Shafranov itself. It's convenient to start with a pure hydrodynamics. We know that in hydrodynamics we have 5 equations: Euler equation, energy equation, and continuity equation, and 5 unknown functions, 3 components of velocity and 1 and 2 thermodynamic functions. But we have some simplification in the case, for example, of the flat two-dimensional flow. If we consider time-independent flow, that we have the conservation of Bernoulli integral, independent of, in the source coordinate, give a constant velocity in this direction. And if we consider ideal flow, the entropy will be integral as well. And well-known example is a flat potential flow. In this case, it's possible to introduce the scalar function phi with a function of to coordinate. And if we consider the case when the Bernoulli integral and entropy are constants in whole space, then the continuity equation and Bernoulli equation results in well-known equation for the potential phi. You see, we have linear elliptic part and nonlinear part containing d very important values which just separate the subsonic and supersonic flow. And what is important, it's maybe one of the key points, that the equation is to be added by Bernoulli equation to determine the sound velocity which takes place here. And fortunately for polytropic equation of state, it's possible to do directly. It's well-known expression. And the property of this equation is well known. First of all, as I said, it is to be added by Bernoulli equation to determine sound velocity. Together with Bernoulli equation, this equation contains potential phi and integrals only. And so entropy in this case is necessary to determine density. For constant density, this equation becomes linear. This nonlinear in general case is elliptic for subsonic flow and hyperbolic for supersonic flow. And what is maybe the next point is the main one. For a given flow structure, that if we know the potential phi and integrals E and S, all values are determined by algebraic equation. Then the Grad-Shafranov equation is actually another version of this equation. Because if we now consider axisymmetric stationary ideal flow, it is possible to introduce another function, big phi, which have the sense of the flux, because you may check that this expression takes place and levels when f are equal to constant give us the flow surfaces, which are axisymmetrical. And there are two examples for expression for phi, for spherically symmetric flow and homogeneous flow. And what follows, we will use these expressions. Of course, in this case we have the same, there is 5 equations and 5 unknown values, but now we have, if we have stationary axisymmetric ideal flow, we have 3 invariants, where are constant of the flux function. Bernoulli integral, angular velocity, angular momentum, and entropy. Then the rest 2 equations can be rewritten in the form of the second order partial equation, which actually is the earlier equation described through invariant. So it's possible to write down the hydrodynamic limit of this equation. Of course, it's rather enormous, but you see similar expressions. Elliptic linear, non-linear terms, what d absolutely the same as in previous equation. These terms correspond to the fact we use not Cartesian geometry. These terms correspond to the fact that now it's possible to introduce the gravity. And these 3 lines correspond to new information, because now it's possible to consider the flow when Bernoulli integral and entropy not constant everywhere by the function of flux, and angular momentum not equal to 0. So it's possible to consider not the helical flows. But the properties are quite similar. This equation contains 5 and 3 invariants only. Elliptic for subsonic flow, hyperbolic for supersonic flow, nonlinear, but what was rather strange for us is previously almost unknown. Previously means we obtained this equation 5 years ago. And of course it has trivial solution, the spherical accretion ejection, if entropy and Bernoulli integral are constant and angular momentum is equal to 0. But as I said, very important property is that for given flux and 3 invariants, all physical parameters are determined by algebraic relations. And new possibilities are that it is possible to include gravity. It's possible to consider more general case, which is just very important for applications. As to generalization to MHD, it's very simple because now we can introduce similar potential, the magnetic flux psi, which determines the colloidal magnetic field. And then if we consider ideal flow, that is Friesen condition takes place, it's a very important point as well because it means that we have plasma enough to screen the longitudinal electric field. Then it's very interesting that it's possible to determine all characteristics, other characteristics, electric field and for velocity, introducing only two scalar functions, angular velocity and the ratio of the particle flux to magnetic flux. And as a result, in this case relativistic but in flat space, we have 5 invariants. Energy, that is Bernoulli equation, which contains not only particle part but electromagnetic part as well. It's actually the flux of Poynting vector. Angular velocity, entropy, angular momentum, entropy, angular velocity, and particle to magnetic flux ratio. And as I said, at first glance, we have the splitting of the problems. That is, as in the very first case, the number of invariants together with magnetic flux psi is enough to determine all characteristics of the flow for algebraic relations. But the structure of the colloidal magnetic field itself is to be determined from the solution of the much more complicated problem. It's necessary to solve the Grad-Shafranov equation. I will show you the last version. What is important that now the understanding gets that actually we have no splitting. Maybe one of the first main points of my talk, that actually we have no splitting. It is impossible to consider the algebraic relation separately from the Grad-Shafranov equation. There are two examples I will have no time to discuss, but it's necessary to mention. First of all, the position of the fast magnetosonic surface for monopole outflow in reality takes place at finite distance from the central object. But if we consider this problem in a given monopole magnetic field, as Michael did firstly in 1969, and later a lot of people reproduced this result, the position of the fast magnetosonic surface moved to infinity. This result isn't self-consistent. If we consider the self-consistent problem, the fast magnetosonic surface takes place at finite distance. And another example, we have the singularity of alphenic surface in the Grad-Shafranov equation, but we have no singularity in the algebraic relations. And what is important as well, the Grad-Shafranov equation has its own problem. I will show you that it's impossible to solve the direct problem in general case. There was the end of physical introduction, and now some mathematical introduction. How it's possible to describe this approach in the black hole case, the curve metric. As you know, the general relativity is necessary to work with 4-dimensional values in curve metric. But there is a very convenient language, 3+1 split, which allows to work with 3-dimensional vectors. Because the only it's necessary to write down the Grad-Shafranov equation, as I said, it's necessary to have the stationary axisymmetric flow. But curve metric of the rotating black hole is axisymmetric and stationary. There is a well-known expression I show it only for clarifying my notations. So the main idea as I said, to use the ZAMAs, that is, observers rotating with angular velocity, length sealing angular velocity around the black hole. In some sense, that is the inertial frame at any rate in 5 directions. For this reason, there are no extra terms in the equation. And what is important is the metric becomes diagonal. It's possible to use 3-dimensional vectors, which can be determined, for example, from local experiments. And as you can see, the expressions for magnetic and electric field and for velocity, as well as the invariant, remain actually the same in the flat space. Actually, curve metric exists here in the Labs function, here as the length sealing angular velocity, and of course, in what follows, we see that it's necessary to use all differential operator in the curve metric. But you see, for example, the electromagnetic part of the Bernoulli integral remains absolutely the same. And here we have only extra adjunction. So as I said, in general case, it's possible to obtain all information knowing invariance and magnetic flux psi. Many people are working in this area, and Semendin was the first who write down this expression, that is expression for Lorentz vector, 5 components of for velocity and electric current flowing in the system in the curve metric. You see, there is very simple limit to the flat space because it only means that alpha is equal to the unit and length sealing angular velocity is equal to 0. You see that this expression contains only invariance and some extra function m square, which have a sense of Alfvénic Mach number. There is a formal relativistic expression, but in the non-relativistic case, it has the Alfvénic Mach number. But as to Alfvénic Mach number itself, it can be determined from Bernoulli equation. As I said, it's necessary to add the Grad-Shafarov equation by Bernoulli equation, which actually is necessary to write down natural expression for Lorentz vector, and then we see that this equation contains only invariance, flux psi, and m Mach number. So this equation gives us the implicit form of m squared. There is knowing invariance and psi, we can determine Mach square as a function of these values, and then use these equations to determine other characteristics of the flow. What is important, this equation contains a lot of singular sophist, Alfvénic sophist, and fast and slow magnetosonic sophist. In what follows, I will consider the cold flow for simplicity. For in this case, we have no fast, slow magnetosonic sophist. And another singularity is a cusp sophist. So I have no time to discuss this in more detail, but as to trans-field equation itself, it can be obtained absolutely by a similar way. A lot of people, as I said, work in this area. But let me stress, this will be my historical introduction, that as to the black hole physics, the core metric, it was obtained only by 2 groups, firstly by Japanese group and 2 years later in our group. And in this point, you see that only two groups could work could consider the properties of the black hole magnetosphere in this approach in the Kerr metric. But as I said, a lot of this equation contains a lot of problems, and both groups, by the way, spend a lot of time not in black hole metric, not in the Kerr metric. So actually, up to now, we have only a few results of the Grad-Shafranov equation in Kerr metric. Let me stress that this form is very convenient because very simple limit to the flat space. As I said, it's necessary to put left function is equal to unit and angular velocity, length-differing angular velocity is equal to 0, and then we will obtain this equation in the flat space. But you see, of course, it's an enormous equation, but you can find familiar terms, that is linear elliptical, non-linear expression, but of course the expression for these values is large enough, but in higher dynamic limits it has the same values as previously. So the main properties of this equation are: it contains psi and phi invariants only, and is to be added by Bernoulli equation. This is quasi-linear. This is elliptical. In this case, and hyperbolic in this case. Sakurai was maybe the first who write down this, who explained this property, that if we have the flow and if we pass the cast surface, slow magnetosonic, alphenic, and fast magnetosonic, we have elliptical here, hyperbolic here, elliptical here, and hyperbolic here. Okay, there is the end of my introduction, and now let's start to discussion. And main point here to clarify the properties, the additional properties for black hole magnetosphere. First of all, we have the second family of critical surfaces. This is well known, but it's possible to demonstrate in the Japanese group pictures when there is a function of contravariant radial components with respect to the radius. You see that we have not only alphenic singularity and the outflow, the positive velocity, but alphenic and fast magnetosonic singularity for inflow. This point is very important because as we see actually, alphenic surface plays the role of semiconductor. It is possible for particle to intersect large cylinder in one direction only, outward for outer flow and inward for internal one. It means that it's necessary to create particles between two light cylinders. It's very important key problem, and in what follows I will use the idea that in the magnetosphere it's possible to have pair creation quite similar to the external gap in radial pulsars. Let me remember that in the radial pulsars there are open field lines where Goldreich-Julian density change sign. So it's possible to have longitudinal electric field here. This longitudinal electric field accelerates primary particles. They radiate the curvature photons and inverse Compton scattering on the X-ray photons from neutron star surface produce hard enough photons which produce finally the electron-positron pairs. It's very interesting that the black hole magnetosphere it's possible to create particles in a similar way, because if we consider the expression for the Julian charge density, we will see a change sign. Change sign as a result of the general relativity. And they are very all transparent when we found the shape of this pair creation region for monopole and quasi-homogeneous magnetic fields. Okay. Another important point that parameter d, I said, is equal to -1 in the horizon. It means the transfield equation is hyperbolic over the horizon. It's a very important point because it means, and we will see that it's not necessary to introduce any extra boundary condition at the horizon. On the other hand, we know that if we use membrane expression for electric and magnetic field, it's possible to describe this expression in such a form, and at first glance, it's the boundary condition at the horizon. There is the same expression in the force-free case. But as Punsley clarified previously, the horizon isn't in causal contact with magnetosphere, so it's impossible to have any boundary condition here. And the answer that any solution of the transfield equation satisfies this equation. Indeed, that fact that we have d is equal to -1 means that we have not hyperbolic and not elliptical, but paraboloid equation. And you can check that all derivative in r direction disappeared. So you may check that it's possible to integrate Grad-Shafranov equation in the surface of the horizon to obtain this expression. So this expression has no sense of boundary condition. And by the way, just the result of that fact I have stressed previously. Because this expression has the sense of the boundary condition if we know psi. Of course, if we know psi, this condition is the connection between the electric current and angular velocity. But we do not know previously the psi, and psi is unknown. The psi is to be determined from the solution. So for this reason, this expression gives us no information, no extra information about the structure of the magnetic field. But as you know, this expression, that fact, that the current is proportional to this bracket, was used by many papers, by many people, and maybe Thorne and McDonald firstly. We see that it's possible to extract energy from the black hole only in omega f larger than 0 and smaller than angular velocity of the black hole, and well-known evaluation of the energy loss of the black hole. As I stressed from the very beginning, it is the problem of evaluation of the total energy loss of the system is the main problem I'm going to discuss, and as I said, let me repeat it, to determine it, it's necessary to define angular velocity and current flowing in the system. And the last point here is the number of boundary conditions. Grad-Shafranov was found very simple expression for the number of boundary conditions of this problem. The number of boundary conditions is 2, because we have second order differential equation, plus I, the number of invariants we have, and minus S, the number of singular surfaces. And there is a simple explanation for the Poisson equation, but let me stress here very important point. It's possible to determine just from this expression. Let's consider the hydrodynamic transonic outflow from rotating body. In this case, it's necessary to know 4 plus 3, because it's pure hydrodynamics, minus 1, because there's only one critical surface, sound surface. That is 4 boundary conditions on the surface of the body for transonic flow. It means that it's necessary to have, for example, 2 thermodynamic functions and 2 components of velocity. And we found the solution of this problem for slow rotating spherical star. But in general case, you see that to determine Bernoulli integral from boundary condition, because it's clear that it's impossible to solve the Grad-Shafranov equation without information of the one letter in this equation, you see it's necessary to know all 3 components of the velocity, but the third component of the velocity is to be determined from the solution. So you see the procedure itself is not direct. And to say the truth, is the general properties of the problem, even in the flat space. There are no direct procedure of solving this kind of equations. And maybe there was a reason that, in spite of that fact, so many people working in this area. Up to now, we have no results. Okay, I have approximately 50 minutes to consider one exact solution. I start with Bogovalov solution, who found the structure of the magnetic field for slow rotation of the sphere with 0 temperature and without gravity. Let me remember, of course, monopole magnetic field is non-realistic, but in black hole physics, people discussed split monopole. There is a well-known picture from Blanford and Znaik that if we have the disk separating magnetic fluxes, so we have monopole magnetic field in the upper hemisphere and monopole magnetic field in the lower hemisphere. So it's possible to determine quasi-monopole magnetic structure. In this case, we have 2 plus 4, because we have 4 invariants, entropy is equal to 0, and minus 2, we have 2 singular surfaces, alphenic and fast magnetosonic. So it's necessary to specify 4 boundary conditions of the sphere surface. For example, psi, monopole 1, particle density, for simplicity is a constant, not function of theta, Lorentz factor, constant, and angular velocity, constant for simplicity as well. In 0 approximation, when omega f is equal to 0, alphenic surface coincides with fast magnetosonic 1, and we know its position as a function of the boundary condition. But if we have the small parameter, this one, it's very interesting that it's possible to seek the solution in the form of small disturbance of the monopole magnetic field, and we will see in more detail in the case of black hole. In this simple case, we have the separation of variables, so theta dependence is clear, and as to the radial dependence, it's necessary to solve ordinary differential equations. This is a linearization of the Grashof-Ranoff equation. This equation has the singularity at the alphenic surface, and it's clear that it's necessary to add only one boundary condition, the boundary condition of the spare surface, and it's possible to solve it. This is the expression for asymptotic of this function. What is important? This part corresponds to the far region. What is very important here? That, as I said, all characteristics of the flow, all other characteristics of the flow, including the invariant L, and hence, very important, the electric current flowing in the system, is to be determined from the solution. This is the expression. Let me explain this point, very important point, in more detail. I know. Thanks a lot. Let's consider dependence of the Mach number as a function of distance. Without rotation, the Bernoulli equation, that enormous equation I demonstrate you, a very simple solution, increasing, and we jump without problem from subsonic to supersonic branches. But if we include rotation into consideration, there is no compensation of nominator and denominator, okay? It's necessary. Okay. In this case, there is no compensation of nominator and denominator in this expression. And you see that in principle, alphenic surface can take place in arbitrary distance, not only here. It's, you may find it from nominator of the expression for current. You see that the ratio of L and omega F, which are both zero for non-rotating case. So this ratio may be arbitrary. And this case corresponds well-known case that we have only one transonic flow, but infinite number of subsonic flow. In the case of Bondi accretion, Parker ejection, you know, only one transonic solution and infinite number of subsonic solutions. But to jump from this branch to this one, it's clear that the position of the alphenic surface is to be somewhere here, not so far from this expression. And for slow rotation, it's only necessary to use this expression, that this point corresponds to the alphenic singularity, and we immediately obtain this expression. Let me stress that it's impossible to determine the current in general case. As I said, in general case, it's impossible to do. But in this simple geometry, we may write down direct expression. Okay. In the very end, I return to the black holes. Let us consider the accretion ejection onto the slowly rotating black holes. That is, let us consider a zero approximation, the monopole magnetic field. It's clear that without rotation, monopole magnetic field is exact solution because all particles will move along radius. So if we have particle creation region, we have two families of singular surface, alphenic and fast magnetosonic for outgoing flow, and alphenic and fast magnetosonic for ingoing flow. These are repeat that expression from the radius of injection of particle creation, as I said. As to boundary condition, we actually have two branches of the Grashof-Ranoff equation. So the number of boundary conditions for outflow is 4, in this part it coincides exactly with what Bhagavala did, but it's necessary to add 4 boundary conditions for ingoing flow. And in principle, it's possible to have the following one: Lorentz factor and density, angular velocity, and psi, as previously. But both for ingoing, outgoing, and ingoing flow. But in our case, it's better to avoid these 4 boundary conditions, but consider the following one. That fact that the psi remains the same, no jump, it's clear. This to 1 corresponds, as I used this transparencies corresponds my talk about 4 years ago. 0 surface current along the pair creation region. But generally speaking, it's possible to have some surface current, so it's possible to add some values. And angular velocity. In the case when ingoing angular velocity is equal to outgoing angular velocity, corresponds to that case that the potential difference which is necessary to produce particles in the particle creation region is much smaller than characteristic potential drop in the system. But in principle, pair creation process can determine us these values. So these values are to be determined from the pair creation mechanism. And we can produce absolutely the same work that is without rotation, m squared. This is m squared as a function of redshift, let function, remains approximately constant, and we have the jump from subsonic to supersonic flow in the moment when m squared is equal to alpha squared, thus correspond to alphanic singularity. But if we include rotation, the position of the fast or position of alphanic surface may be in arbitrary place. But if we again use the nominator of the expression, relativistic expression for the current, we can determine these values. And absolutely by the same way, we can conclude that to have transsonic flow, that to have the possibility to jump from subsonic to supersonic flow, alphanic singularity is to be somewhere here, this expression. And we immediately obtain this expression for A. And now, if we propose that there is no surface current in the pair creation region, it means that L plus is equal to L minus. So, using this expression in the ingoing singularity and appropriate expression in the outgoing singularity, we obtain the expression for angular velocity. This is the key answer of the problem. It means that in pure hydrodynamics, for transsonic or double transsonic flow, not only the current, but the angular velocity itself are to be determined from the solution. And it means that that expression for the energy loss now is determined from the solution. Of course, this expression corresponds to that case I discussed. Thanks a lot. That is, we consider a very small potential drop in the pair creation region. We consider the case when there is no surface current in the pair creation region. In this case, we obtain well-known results, many people. But let me stress that it's not evaluation, it's a solution, which is possible to obtain in this simple geometry. In general case, as I said, it's impossible to do. Of course, if we use more realistic expression for potential drop in the pair creation region and surface current, we will obtain some other expressions. But it's possible to do. There is the only new points I did last 2 months is a direct expression for the equation of the disturbance, the generalization of the Bogomolov equation. For simplicity, this case corresponds to the constant but opposite in sign expression for eta and energy. But nevertheless, we have 2 equations because you see this term and this term change sign in ingoing and outgoing region. But what is very important, that this equation contains no singularity at the horizon. This term, this, and this contains lapse function, and you may check that these 3 lines also vanished at the horizon. So there is no singularity. There is no singularity of the horizon. It's clear that this equation is linear, and you see the sign dependence remains the same as this eigenfunction of this operator, so it's possible to solve the solution absolutely in a similar way. And as to equation for radial function, we didn't solve it because not important. I only discussed the general properties. You see, this equation contains 2 singularities, the internal and external Alfvénic surfaces, and but we have, for this reason, it's not necessary to add any boundary condition to have the solution passing smoothly through the fast these Alfvénic singularities. And as to the moment of the pair creation region, these 2 boundary conditions just instruct us how to do in this point that we have no discontinuity of radial function and no discontinuity of derivative. So it's possible to find the solution. Okay, conclusion. For double transonic flow, not only current, but the angular velocity as well is to be determined from the solution. There is a result of careful consideration of the problem. Secondly, horizon doesn't affect the solution. It, as is necessary, then not in causal contact with the magnetosphere, and for this reason, it doesn't play the role on unipolar inductor. Nevertheless, the whole system works as a unipolar inductor, and the properties of the pair creation region, that boundary condition I have discussed, determine the energy loss of the black hole magnetosphere, because just this boundary condition, the properties of the pair creation region, determine us the values of current and angular velocity. And knowing current and angular velocity, we know all properties of the flow. Okay, I have no time for some last remarks, but I have time to the general conclusion, which was my conclusion of that 5 lectures I said. The general conclusion of the possibility to use the Grad-Shafranov approach itself, not only in connection with the black hole physics. Unfortunately, the problem of collimation, particle acceleration, current systems, and external energy are not solved yet. One of the reasons, in general case, it is impossible to solve the direct problem. It is impossible to determine the flow structure for physical boundary conditions. Not to say that this approach cannot be generalized in a non-stationary, non-axisymmetric, and dissipated case. As a non-stationary case, I hope that Professor Chechotkin will discuss this problem, but absolutely not clear that stationary, that time-independent solution we'll discuss, and many people discuss, are really stable. is a very important problem, and unfortunately it's impossible to generalize this approach to the case of non-stationary. Nevertheless, some model solution was obtained, even for direct problem. Some model solution was obtained even for direct problems, but for simplest geometry, and they clarified many key properties. For example, the number of boundary conditions, as I demonstrated in the simple example. And the last point, that all solutions was obtained up to now are too far from real astrophysical sources. Grazie. I said that from astrophysical point of view, the result was no, because it's clear that angular velocity omega f is to be of the order of omega h, black hole angular velocity, 1/2, as I said. Here, in the simple geometry, we obtain this result as a solution. Of course, it depends upon geometry, for example. For non-monopole magnetic fields, angular velocity will be... It depends upon, it's approximately equal to that of black hole angular velocity. If you know the angular velocity... No, it's unknown because we do not know the real angular velocity of the black hole.
We don't see the prediction for black hole, for acceleration, for figure acceleration, which we observe 200 years, 180 years. We don't see any prediction.
These are the result of rotation.
Yeah, for example, if you make acceleration,
it's another problem, because I discussed the properties of the magnetosphere of the black hole with a given angular velocity. But angular velocity of the real... okay, you say that in reality omega f is very small. Okay, no problem. Yeah, okay. No, I said that some people tried, and last year I just working in this area to try to move outside this approach, but it's also possible to do only in some simplest geometry, but approach itself is very bad. Maybe it's necessary to add. The Grad-Shafranov approach is very bad in that sense. It's impossible to generalize. And what is necessary to add, of course. By the way, all people trying to work numerically work not in the Grad-Shafranov approach. They solve the time-dependent code because it's much easier to consider time-dependent problem than to solve the Grad-Shafranov equation and the position of the... Because we do not know the position of the critical surface. They are to be determined from the solution as well. And for this reason, it's absolutely impossible to solve the problem where we do not know the surface when the critical condition is to be specified. Of course, it's necessary to add this point.
Some of the complicated solutions that will survive.
Only in the simpler geometry is possible.
Okay.
it on now? I'm going to mostly talk about some highly phenomenological subjects which are related to the gamma ray burst phenomena. So as you already probably heard about this many times at various places, this subject has been a very interesting and exciting subject for many reasons. And so I'm not going to actually cover the entire field, and I don't think I have much time, but I want to actually emphasize just a few things in this field, which is to me related to actually a series of works I've been doing in the last several years. First of all, I'm going to mostly talk about gamma ray bursts generated by pulsars. So as we already were told by many speakers, pulsars and black holes are in many respects share some similarities. For example, a given pulsar would be given a rotation with a strong field, and a black hole could be equally strong in its magnetic field, although it's not self-generated. In a sense, magnetic field cannot be due to the black hole itself. It has to have some sort of a plasma around it. So most of the phenomena we have to describe in trying to build a model for gamma ray burst in the case of pulsar is similarly related to the black hole physics. There is one fundamental difference. That is, in pulsar's case, we can actually make all these numbers, time scales, energies, and things like that in place without resorting to any actually outstanding uncertainties. We already know what pulsars are. We already know actually what pulsars can do, and we already know actually what plasmas could do around pulsars and black holes. So the reason actually I'm talking about pulsars is because of the three reasons I listed down here. Before that, the talk I'm going to give you today is based on the works that I've been doing with the various collaborators of mine listed here: Chung-Lee Kim, who's a research student at Ihwa, and Chongman Yang, who gave a talk yesterday here, and Josh Grindley, and he's mostly working with me on the connections between millisecond pulsars and the gamma ray burst. And Craig Wheeler, Peter Weflick, and Lifan Wang, they're actually working with me on gamma ray burst supernova connection. And Eric Blackman, who's at Caltech, who's doing actually most of the theoretical works on pulsars with me these days. So with due credits given to them, I'm just going to summarize what actually issues and developments I'm going to focus on today. These days, actually, people talk about gamma ray burst as phenomena related to massive stars. Massive stars being as massive as like a few to probably tens of solar masses. The reason actually they relate gamma ray burst phenomena to massive stars is because massive stars produce relatively massive remnants. That is to say, black holes and neutron stars. So pulsars, as we know, are produced or remnants of some massive stellar evolution. So if you have massive stars forming in an early universe or relatively recent universe, you can expect that actually these pulsars would be related to rapid star formation region, because massive stars would evolve on a time scale less than probably a few tens of millions of years. So these stars would be correlated in position and time with whatever activities associated with this action. So normally what they do in phenomenological
gamma ray burst rate, because there will be essentially on cosmological time scale, there will be no burst explosion and the star formation. It's essentially nothing compared to the.
And then the most exciting discovery in recent study history is the claim yet to be proven 100% at the 100% level that the gamma ray burst might be correlated with the supernovae. It's an exciting
story because we, in the last decade or so, argued very strongly that gamma ray bursts cannot be coming from supernovae because gamma ray bursts require much higher energies than supernovae. But now actually with this, although not so complete or final suggestion that gamma ray bursts are, at least some of them, are connected to supernovae, we might have to reconsider what kind of energies we need in explaining gamma ray burst phenomena. And the third thing is related to actually first and second. If you argue that some of the gamma ray bursts are coming from pulsars, or at least actually energetically not so favorable sites, like black holes with not so strong fields or not so strong spins, as we already will know, then you have to consider whether the gamma ray bursts detected have anything to do with the isotropic luminosity. That is to say, if the jets or outflows are strongly beamed towards certain directions, we might actually see these bursts as energetic as we observe, but they may not be actually such a strong catastrophic event. So what I'm going to say is that actually essentially you can generate this kind of gamma ray burst-like phenomena without requiring 10 to the 51 or 50 erg per second kind of luminosity in the end. You might need only just 10 to the 47 or 48, which is comfortably within the range of supernova physics. So that's what I'm going to say. But physically, what all these issues mean is unclear. The reason is supernovae are different from gamma ray bursts in many reasons. First, supernovae have a lot of junks flying around. So if you want to make gamma rays have to escape from this emission region without being blocked by this dense material. So gamma ray bursts traditionally have required some region free of these baryons, so what they call is baryon contamination. But supernovae are the worst kind of objects you want to consider for gamma ray burst production. And second, if you want to have gamma ray bursts, you want to have actually a lot of energy still in gamma ray range. But supernovae are known to produce most of its energy somewhere not in the gamma ray range, as you'll know. So we have to consider some physical channels through which gamma ray bursts are produced, as well as actually supernovae explode. And then, while doing so, we have to have actually some pulsar generation mechanism or black hole generation mechanism. But I don't think actually I know much about actually how the black holes form from supernovae. So I'll actually concentrate on millisecond pulsar kind of formation, especially the pulsars with rotation period of milliseconds. The reason is simple. If you do not have pulsars spinning as fast as with a period of milliseconds, you will not have enough rotation energy to power the gamma ray burst. And so, why is millisecond pulsar so interesting? First of all, time scale is just right. Millisecond is a very interesting time scale for gamma ray bursts. Gamma ray bursts are actually a phenomena with the total duration of events ranging from milliseconds to hundreds of seconds. So it may be a very heterogeneous group of events, but at least the short gamma ray bursts are characteristic of actually this kind of time scale, which happen to be the millisecond pulsar time scale. Energy is about right. If you actually believe that the supernova energy, total supernova energy, is up to actually 10 to the 50, including all the energies coming in the neutrinos, the energy coming from the millisecond pulsar generation during the supernova collapse would be about right. And also, pulsars are known to produce beamed emission, and at least in radio. So if you believe in that the energy generation in pulsars has something to do with the beaming, then actually pulsar is a very good one, already known to have some sort of a beaming going on. So that's mostly what I'm going to talk about, and then I'm going to mix at various stages the conventional supernova picture with the less conventional accretion-induced collapse. That is, white dwarfs collapse to neutron stars by accreting mass, thereby going over the threshold. So in this case, by accretion-induced collapse, AIC, I mean the explosionless or non-explosive
collapse of a white dwarf to neutron star, but essentially the energetics is the same. So what is accretion induced collapse, which are the core collapse of supernovae? Or we have been trying to do that.
So accretion induced collapse is a process during which a white dwarf, which is accreting from a secondary star, collapses to neutron star. It's not a new subject. We have been talking about this, although there is not a single evidence that this process occurs in the universe. So what people actually half-jokingly argue is that gamma ray bursts are the accretion-induced collapse events. We haven't seen them because we didn't know actually what these are. But now, if you somehow connect the accretion-induced collapse events to gamma ray bursts, you might be able to say that actually what we have detected in terms of gamma ray bursts are the accretion-induced collapse events. So what is it? What happens is you just have a just ordinary, but some sort of a more massive white dwarfs around at least 1.3 or even higher solar mass masses. And then you actually have a secondary star around it. And then the mass accretes from the secondary star to the primary. In this case, it's a white dwarf. And if the mass approaches close to 1.4 solar mass, then white dwarf will reach this critical Chandrasekhar limit, and it will not support itself against the gravity. Once that happens, you expect that actually the size of a white dwarf will collapse into a size of neutron star. But one critical quantity we have to worry about is actually the required accretion rate, that is the mass flow rate into the white dwarf, has to be very high. So high that actually one normally do not think this kind of accretion rate in binary systems. In terms of a definite number, I just chose 5 times 10 to the minus 5 solar mass per year, which is pretty high. And now, if you actually consider a white dwarf with a characteristic set of numbers, that is the moment of inertia of a white dwarf, I sub WD, that's about 10 to the 51, which is a number we normally associate with a white dwarf, and the radius of white dwarf about 10 to the 9 centimeter, and the rotational frequency of white dwarf, which is, in this case, I took 10 to the minus 2, which is very high. So if you give this kind of white dwarf about 10 to the 9 Gauss, then after the collapse, under the assumption that the angular momentum is not going to be lost while collapsing, so angular momentum conservation, and the magnetic flux is frozen into the plasma, then what you get after collapse into a neutron star is going to be 10 to the 15 Gauss, 10 to the 45 moment of inertia, 10 to the 6 centimeter radius, and 10 to the 4 angular rotational frequency. So this is what we expect. But there's one problem here. We have never seen any white dwarf with a magnetic field as strong as 10 to the 9 Gauss. But as you will know, without achieving 10 to the 15 Gauss, pulsars will not be interesting for gamma ray burst emitters. And there's not a good evidence that most of the white dwarfs, at least when they initially began, have rotational frequencies as high as 10 to the minus 2. So comparing that to gamma ray burst, what do we require? This is the same old number you've seen many times in many papers and talks. Gamma ray bursts are basically energetically about 10 to the 51 erg per second event, assuming that energy generation is isotropic, emission is isotropic, which depends on, of course, the cosmology, the redshift of the event, and the Hubble constant and things like that. But it's more or less a solid number. And another headache actually in gamma ray burst is actually time scale. Why is the time scale so widely varying? It could be as short as actually 0.01 second, could be as long as actually up to 1,000 seconds. Why is this time scale so different? That's been a main problem in this field. So if you have a pulsar, before going into that, I want to actually emphasize one fact. If you actually allow the source evolution of gamma ray burst, which mimics the star formation rate, what do you expect statistically? You don't expect anything. The detected gamma ray burst number at about now 2,000, and it's approaching 3,000 pretty soon. But these gamma ray bursts
do not actually tell you whether star formation rate is statistically supported or not. So it's at the level of actually 2.5 sigma level. That's what we found at least. And is there any signature for beaming? No. Beaming you expect actually something very complicated, but in terms of statistical signatures, beaming only induces the luminosity function because the beam directed towards you would appear very bright. Directed away from you, away from the line of sight, would appear less bright. So it induces an apparent luminosity distribution. But that kind of induced luminosity function, apparent luminosity function, doesn't affect the statistical signatures in gamma ray burst. So unfortunately, at the level of 2,000 gamma ray burst, you don't expect more than 2.5 sigma or so signatures in this. But I have something more to say, but it's rather involved, so I'm not going to say this. The reason I brought this issue up was because in the end, you might want to actually prove this or disprove this assertion that gamma ray bursts are beam radiation emission from pulsars. You sooner or later have to resort to some kind of statistical arguments, but that's just plainly impossible at this stage. So what do we have from millisecond pulsars? It's, if you want to go into details, this subject would be very complicated. But basically, at the level of just energetics and time scale, it's very simple. From millisecond pulsars, you expect only essentially two channels of energy emission. One is gravitational radiation emission, when the pulsars develop non-zero quadrupole moment. That is to say, it rotates with an asymmetric shape. So triaxial shape would be a good example. In that case, you expect up to well over, actually 10 to the 50 or 51 erg per second, but in an invisible form. It's a gravitational wave, so you wouldn't detect them. But it all depends on this parameter epsilon here. Epsilon is actually how distorted the star is from the perfectly spherical shape. And another channel would be electrodynamic, electromagnetic radiation. Normally we assume dipole, but we don't know whether the pulsar magnetic field is dipole. Although it's not really entirely crazy, but the magnetic fields around pulsars are not proven to be dipole. But if you take a dipole number, then the luminosity would be about 10 to the 50 to 51, depending on the magnetic field strength. So as I told you before, the required magnetic field and the rotation are 10 to the 15 and 10 to the 4, which are extreme numbers even for pulsars. So if you actually want to talk about time scales, gravitational radiation emission time scale, T sub GW here, is about right. 3 times 10 to the minus 3, which is going to be about the shortest time scale you expect in this kind of pulsar system. And then there is electromagnetic time scale, which is unfortunately very long if you write it this way. I intentionally wrote this way because I chose a number for the magnetic field of 10 to the 12 Gauss rather than 10 to the 15 Gauss. If you put in 10 to the 15 Gauss here, you will reduce the number substantially, which falls right into the observed gamma ray burst duration range. But the reason I wrote in this way is clear, it lacks transparency. So, is gravitational radiation relevant for gamma ray burst? Yes and no. Gravitational radiation itself has nothing to do with the detected energy in gamma ray burst. But it is interesting because pulsars still can spin down while emitting gravitational radiation and electromagnetic dipole radiation. So it spins down quite rapidly while emitting dipole radiation. But the overall time scale is controlled by gravitational radiation emission rather than the electrodynamic radiation. So it could spin down quickly with a lot of power, but most of the power could go into gravitational radiation. Only 1% or less of the energy of this enormous 10 to the 55 erg per second luminosity would appear as gamma ray burst, like gamma ray burst energy. So it's an interesting number. So when does this actually gravitational radiation emission happen? That is pretty clear because of the decades-old study by Chandrasekhar and the later elaborated on by many others. It's clear that the pulsars would emit gravitational radiation by distorting its shape into non-axisymmetric shape at a critical period. So if the period of a pulsar is shorter than this critical period, which is about millisecond here, you expect that gamma ray burst would probably arise from this kind of rapidly rotating and wobbling millisecond pulsars. So what do you get from here? Very simple. If you have a pulsar rotating faster than the critical frequency, or a period shorter than critical period, you expect the time scale of this spin down would be gravitational time scale. So gamma ray burst spin down, duration would be the spin down time scale on the gravitational radiation time scale, which is short. As short as actually a fraction of a second here, right here. And then the luminosity will be still in gamma rays given by electromagnetic radiation. And second, if the pulsars rotate slower, slightly slower than critical, then there will be no non-axisymmetric distortion. And then the electromagnetic time scale would be the time scale because gravitational radiation emission doesn't work. But still the luminosity would be the same. So I think it's just purely based on these simple numbers, originally strongly advocated by Vladimir Yusov, these numbers are still very interesting. And even more so because of the recent attempt to connect the gamma ray burst to supernovae. So what do we know about these millisecond pulsars without explosions? That's actually a question in this class, which I call. So normally this kind of explosionless, silent, electromagnetically silent collision is expected in a particular type of white dwarf, which is called oxygen neon magnesium white dwarfs. This kind of collapse would be expected if the essential density of the star exceeds certain critical density written in here, which is actually right density for magnesium in terms of the electron capture. So once the electron is all captured by magnesium, there is no electron-supported degeneracy. So the core will collapse. This will happen, as I said, at a pretty high accretion rate, but normally these accretion rates are not expected. So that's the reason why we might not see this kind of events very often. So once these events are progressing, what do we expect? We first have to expect what happens right before the collapse. Right before the collapse, you expect to have a white dwarf massive enough to collapse, but it's rotating rather slowly. So before this collapse happens, we have to specify what is the condition prior to collapse, because everything is conserved during collapse, which is happening on a gravitational dynamical time scale, which is short. So we assume that angular momentum is conserved and magnetic flux is conserved. So we have to specify that. But fortunately, we pretty much know actually how this white dwarf spin is evolving. That is, white dwarf is actually getting mass as well as angular momentum from accreting mass, and then it actually also gets torque from the plasma, which is connected, accreting plasma, which is connected to the star through magnetic field. So I'm not going to go into this detail, but essentially this equation tells you the mass accretion and the size change because of white dwarf's mass change. As the white dwarf's mass changes, radius changes. There is a well-known mass-radius relation in white dwarf cases. And you have actually this N, which is the torque acting between the accreting plasma and the star. So it's pretty much well-known standard thing. And white dwarf's magnetic field will respond to the size change by attempting to conserve its magnetic flux, so flux conservation. So if you do that, you pretty much know what will happen to the white dwarf while accreting a lot of mass. So the detailed calculations I'm not even go into, but just basically a very heuristic expression here is sufficient. That is, white dwarf right before the accretion index collapse will have about 10-second period. It depends on the white dwarf magnetic field strength and the mass accretion rate. but we already know what the master cushion should be and what the magnetic field dependence is. So we're pretty much sure that actually it has to be about 10 seconds or so. But this is subject to some other technical uncertainties, but I'm not going to talk about it. So if you actually let that kind of white dwarf collapse into a neutron star, what do you expect? You expect about this kind of millisecond pulsar. That is to say, on top here, the millisecond pulsar's rotation frequency will be about 10 to the 4 if the magnetic field is about 10 to the 11. So the pre-collapsed white dwarf will turn into a 10 to the 11 Gauss, 10 to the 4 Hertz frequency millisecond pulsar with a number here, uncertainty ranging from 2 to 6, the factor of 3 essentially. So I'm not going to explain this factor of 2 to 6, which unfortunately has some things to talk about. But basically what I can assure you is that actually this is a very solid correlation between the magnetic field and the milliseconds pulsar spin. Now you have a pulsar, millisecond pulsar, and you want to produce gamma ray bursts by essentially letting them use their rotational energy. How do you describe it? Unfortunately, this is another massive question. It's been worked on for many, many years, but I don't think actually there is any essential improvement because of the large dynamical range of these numerical calculations. But what we can do is to borrow the original calculation from Chandrasekhar modified by the strong magnetic field. That is, I'm not going to go into these equations, which is meaningless in this. We actually have a pulsar with the three radii.
Remember, it's a triaxial shape. So rotation axis is in the direction, one direction here, and 2 and 3 directions are perpendicular to the rotation axis. And these 3 radial extents of a star, they are triaxial. 2 and 3 are directions perpendicular to the rotation axis.
Then is described by these 2 equations.
So here L's mean the ratio of 2 radii with respect to the size of the star along the rotation axis. And if you actually have this nonlinear differential equation, it's just simple to solve this. If you just solve it coupled with the magnetic field, because we want to know how the magnetic field also changes while the star is spinning up or spinning down. So what you have is actually a set of dynamical equations described for the star. But while the star changes its shape, essentially what happens is that a plane perpendicular to the rotation axis changes its effective area. So the magnetic flux threading the star in this plane would change. So if you allow the flux conservation, then what you have is the magnetic field strength change, because you said that actually there should not be any flux change. So it's exactly the same as in just area calculation. What you have to worry about is the triaxial shape. So if you do a little bit of manipulation, assuming that the magnetic field maintains a dipole shape, then what you get is essentially this expression here. That is, the magnetic moment along this one axis, this is the rotation axis, is mu star 1, which is actually a simple function of a geometric shape. And R bar is a sort of mean size of the star. So the geometric ratios of these, this is the geometric ratio of this dimensionless radii I defined in here, right here. So 2 to 1, 3 to 1 axis ratio. And then there is only one complication, that is the magnetic moment along the rotation axis is just completely specified by just accident, complete elliptical integral of second kind. So you actually have this expression so that as soon as you solve these 2 equations, you know how the magnetic moment changes. So after all doing this, it turns out that
the electromagnetic power as the pulsar spins down doesn't change a lot by this geometric effect. Before doing these calculations, we had no idea, but after doing this, the effect arising from the changing effective cross-sectional area of a star is only at the level of factor of 2. So mostly the electromagnetic power is affected by the spin down, as in ordinary calculation, without considering the star's a shape change.
Can I ask a question about that?
Yes.
When you improve the small reflection section, do you have that kind of control with the exponential shape?
Actually, that's the question which I try to avoid. So actually, if you have this back reaction curve from gravitational radiation, you're not guaranteed to have a homogeneous ellipsoid without any density structure. There could be actually some internal velocity structure too. Then you cannot actually describe this kind of shape with a homogeneous ellipsoid. It has to contain some other physics, which is what they call is a other spheroid structure, but we haven't done that. So back reaction is important. So after just describing what happens to the magnetic moment of the star, you obviously can write down this expression. That is, electromagnetic luminosity, power, is just the magnetic moment defined along the rotation axis squared times the rotational frequency to the fourth, which is exactly the same expression as you expected. So the gravitational radiation timescale, which I defined or showed, and electromagnetic timescale are all in here. So if you just include this expression and then combine this with the, if you remember, the magnetic field to spin correlation, which I defined, if you remember that, then you can actually write down a single expression which is unique in this picture. That is here. So if you combine the top expression with this correlation between omega and B, then you eliminate 1, obviously. So what you have is a pretty obvious expression, that is electromagnetic power always comes out as a number which depends only on the magnetic field or rotation. So electromagnetic power is 10 to the 44 erg per second times omega star over 10 to the 4 to the power of 3 halves. So what is this number? This is pretty small compared to the gamma ray burst number. So if you believe in nothing but this very classical picture of a the white dwarf to neutron star collapse and then spin up and then spin down by gravitational radiation emission, you expect only about 10 to the 44 with a definite dependence of like this. And the spinning down will happen on a gravitational timescale. So what this means is that the electromagnetic radiation emission timescale is too long to be compared with the gamma ray burst emission timescale, which is only a few seconds, let's say. So we introduced a couple of years ago, and Professor Lee also talked about precession. So now if you have actually certain beam shape which is well collimated, then binary systems could actually interact with each other. So this beam is not going to stay steady in space and time. It will be affected as the jet base, which is connected to the star, would be affected by the other things, secondary star, for example, in binary systems. So we expect that there will be a jet precession. So if the jet precession happens, then even if the beam is steady and emitting the radiation for a long time, the beam would actually sort of wobble out of and into the line of sight. So it could actually produce some apparent short time scale events with some various interesting variability properties. But I don't want to go into this detail, but there are at least the 3 well-known mechanisms which are listed in here, but I'm not going to talk about it. I don't have much time. So at least there is a mechanism which can actually prevent this kind of long time scale from being a problem for gamma ray burst emission mechanism. So if you actually, I'm not going to go into this detail, but if you actually demand that observed 1 second, 10 second duration has to be related to this kind of definite mechanism, then you have to have a very sharply beamed gamma ray burst. So that beam size has to have a very narrow width. So that translates into this kind of constraint. And again, if you have a beam, one ordinary objection to beam picture is that it will repeat itself. But it's not the case, because actually there are different precession mechanisms which will prevent the repetition of the same kind of beaming coming into your line of sight. So that's not really a problem, as long as you have a certain constraints on the binary system parameters, which I wrote down in here. But I don't think it's particularly interesting for you at this point. So what happens once actually this emission happens? So electromagnetic dipole radiation is in the form of just pure Poynting flux. So it just flows out. It has nothing to do with a gamma ray burst in that form. So it has to convert itself to a gamma ray burst. So what we advocated was exactly what Vladimir Yusov has been arguing for. It's a very nice, well-defined picture, except the fact that if you have a lot of baryons moving around, this mechanism would fail. I'll explain it just briefly, which is a little bit involving. That is, if the Poynting flux flows out, then it's essentially oscillating electric field flowing out. It has nothing to do with the dissipation. Gamma ray bursts have to arise from dissipation of this pure wave form of energy. So what happens is that in this Yusov's original picture, and due to actually earlier papers, but in this present form, this first, as far as I know, was written by Yusov. That is, after actually this plasma coupled with these waves flow out, there's a certain radius at which the density becomes low enough that the current cannot be sustained. So once the current is not sustained, then you cannot maintain a perfect MHD-like condition. So something like a particle creation should happen. That happens exactly when the intrinsic plasma density falls below the classical Goldreich-Julian density. That's the density at which first the current, which is required to support this wave motion, is breaking. So you just cannot sustain that activity at this radius. In the parameters we just talked about, 10 to the 11 Gauss, 10 to the 4 for the spin frequency, you essentially have about 10 to 12 centimeter. That's not far, but that's far enough from the center. That is about 10 to 6 centimeter. So you will expect, in this case, a relatively baryon-free region where this picture is relevant. I'm not going to go into details, but essentially in this picture, what happens is once this actually radius is reached, then there will be particle creation in terms of pair creation, electron and positron creation. And these electrons and positrons gyrate in magnetic field, and it produces synchrotron photons. And these synchrotron photons collide to themselves, their parent electrons and positrons. So it's a synchrotron componization process. So it's self-componizing synchrotron-produced photons, and in doing so, it reaches a very high energy, essentially about the energy of the electrons and positrons, which is about 10 to the 10 to the 20 hertz. That's about gamma rays. So I didn't even actually bother to write down the expressions, which is meaninglessly complicated in here. But what I can tell you is that the spectrum expected is characteristically at around the frequency of 10 to the 20, and its tail could be as high as at 10 to the 24. So it's about 1 MeV to 1,000 MeV range. So that's expected. Okay. So if you actually have gamma ray burst, then what happens is that this frequency here, synchrotron frequency here, has to be in the right range. That is to say, observed 1 MeV range. But as I already said, this arises naturally. So what I wrote down in here is that the required gamma ray burst emission tells us that the pulsar has to have this kind of a relation. That is, the spin frequency has to be comparable to the magnetic field in this relation. So the gamma ray burst generation in this picture is never a problem. It just comes out naturally. Then I think if there's an interesting question which I addressed with the Josh Grindley, that is millisecond pulsar rate interesting in reverse rate? Actually, the answer is no. There's only one way to get out of here. That is, the millisecond pulsar observers have tried to estimate the millisecond pulsar birth rate. Pulsars spin down and then disappear as millisecond pulsars because it loses rotational speed. So what we expect is about the rate of 10 to the minus 5 per year per galaxy. That's based on the pulsar's lifetime of detected the millisecond pulsar. Burst rate, assuming that gamma ray bursts are homogeneous, then you expect about 10 to the minus 6, a few times 10 to the comparable, but it's not the same. But I think that there is a
problem here. That is, this millisecond pulsar birth rate was based on the magnetic times 10 to the 8 Gauss. But the kind of pulsars we are talking about is actually pulsars with the 10 to the 11 Gauss. So their spin down time scale through electromagnetic radiation emission will be much shorter. So you actually have the millisecond pulsar birth rate, which is actually as large as this, but it could be actually even bigger. So if you compare that to the gamma ray burst rate, then there is one way out of this problem. That is, gamma ray bursts are intrinsically very sharply beamed. So you need a lot more gamma ray bursts than isotropic case because you detect only a certain fraction of it. Then you can compensate for that by assuming that the millisecond pulsars are born with 10 to the 11 Gauss. But we know that actually most of the pulsars we detect have magnetic fields less than 10 to the 10 Gauss. So what we argue eventually is that gamma ray bursts are arising, if they have to, arising from millisecond pulsars with intrinsically very different magnetic field strength than most of the ordinary millisecond pulsars. So I think it's a reasonable conclusion, but there's no way we can actually prove it at this point. So now actually I want to just finish with one interesting thought me and Eric Bregman has been advocating, but there are some problems which I hope I can address in a very short time. That is, if the pulsar spins very fast, then actually there is a competing mechanism for magnetic field amplification. Not only just flux freezing through the contraction, but also the internal dynamo mechanism. So there are three critical frequencies based on what we already talked about. That is, stellar frequency, pulsar's frequency, and omega critical, which has something to do with the gravitational instability, and the dynamo frequency. So if the star rotates faster than a certain period, then internal dynamo would trigger in. So what happens is you have three cases. You have three cases in here. That is, star spins faster than the gravitational limit. So it's emitting gravitational radiation. So it's above all the interesting frequencies. In this case, develop magnetic spinning. The star spins fast, but not so fast, so it doesn't have gravitational radiation emission, but it has a strong field through dynamo process. The third process is it's just so slowly spinning that it doesn't have anything to do with the gravitational radiation. It doesn't have any dynamo mechanism working. Have a strong, not so strong field, and the time scale will be long. So you essentially have these three populations, and one gamma ray burst with relatively high luminosity. One will be a gamma ray burst population with relatively comparable but slightly less luminosity but longer time scale. The third one, gamma ray burst, which might be more relative to supernova event. So if you combine this idea, then we essentially can define three classes. One is super
gamma ray burst essentially rotating fastest, and will be that is going to be rotating slightly less, and then there will be weak gamma ray burst, but it will essentially have something to do with the supernova explosion. So this is mostly what I talked about, and I'm skipping something in here. And do I have about a minute or two? Okay. So this is, so I'm just going to finish up with this idea. So gamma ray burst we talked about. So we more or less expect what would happen if the gamma ray bursts are due to millisecond pulsars. But these days, people are talking not only gamma ray burst, but also after gamma ray burst. But after gamma ray bursts disappear at the same locations in the sky, you see optical, radio, and some X-ray signals. So the picture is gamma ray bursts were emitted at the center, and somehow the leftover energy moves out, and there will be more energy coming out at the at larger radii. So if you have a pulse center, what happens is this is not entirely disruptive. Very to have some leftover any energy source at the center. Most of the emission after gamma ray emission stage will be determined by projected during the explosive stage. But if you have a pulsar left over in here, then the explosive energy phase ends, then you will be eventually taken over by the energy injection from the center. That is actually what I mean by afterglows with the millisecond pulsars. So this millisecond pulsar will inject energy in just too little energy coming out. So if you have this kind of millisecond pulsar sitting at the center, what you expect is this, essentially, just right here. So if you have a very fast-spinning millisecond pulsar, initially it will be spun down by gravitational radiation emission. So during that stage, whatever energy comes out from the center will t being the time scale, the duration of the event. But after about suddenly the energy injection from millisecond pulsar will sort of go down much faster than t to the, in essence, it's t to the minus 2. So you expect the decrease of luminosity described by a sort of broken power law in time. But if you have a millisecond pulsar which has nothing to do with the gravitational radiation emission, it will essentially remain constant as long as the electromagnetic radiation is interesting for gamma ray burst. That's here. And then after that, it will be broken into t to the minus 2. So have much steeper decrease in luminosity. But millisecond pulsars could do a similar thing in here. So I'll just put on the summary in here. I didn't have much time to cover the supernova connection, but I can summarize it in one sentence. That is, supernova, we've done complicated considerations, but it in essence requires to get rid of the high density environment, at least along the rotational axis or jet axis. That requires jet power of about 10 to the 52. So, in isotropic case. So if the jet is very highly collimated, then the supernova will form, and then there will be the compact object at the center, but the envelope of the progenitor star will sit there. But you have to first lift them up out of the along this rotation axis, and then there will be this electromagnetic dipole radiation, just like in black hole picture and neutron star picture along this rotational axis. But this axis has to be cleared if you want to have gamma ray burst. That's actually most severe constraint on the supernova picture, but in most cases, the energy-wise, it's not a problem, but in essence, it has to be seen whether actually that kind of heavy MHD type jet could be produced right at the time of a supernova collapse. So that's an option we have to look for. But if it's gamma ray burst, then I think we already found them. But it's unclear whether all supernovae have something to do with gamma ray burst. So I'll just finish right here. I understand. Actually, I think I'm not sure about that number, where that number came from, but I thought that the number has to be about 10 to the minus 4. So I agree. If you have too many gamma ray bursts, then I think that there will be little chance that this galaxy would have any life form. But you can actually say just destroying life forms. But if you have a thick liquid like water, so that So you mean you're talking about whether the scattering region could be approximated by adiabatic or not? Sort of. I think originally this particular exactly.
So